Do you struggle with the concepts of thermodynamics? Is the math and the symbolism just too much to bear? Is your prof going through at a breakneck speed and never looking back? Well, I've put together a whole course and series of videos on thermodynamics that takes you from the very beginning, step by step, and works you all the way up to the questions that you'll see on your final exams. My name is Terry, and I love thermodynamics, and I'm super excited to share my knowledge of thermodynamics with you. We're going to start at the very beginning with this video and go over some introductory concepts and then build from there so you'll get a solid understanding of thermodynamics and not just some weird, confused journey that you don't know which way you're going. So let's begin. Now, at the very beginning, we need to discuss what the meaning of thermodynamics is. Then we're going to discuss work. And then we're going to talk about state variables and equations of state. And then finally, we'll talk about ideal and real gases to give a beginning of learning thermodynamics. Thermo comes from the Greek word therm, meaning heat. And dynamics comes from the Greek word dynamikos, meaning powerful. And that's how thermodynamics was born. It was born to harness the power of heat to do useful things, like power trains, for instance. But nowadays, thermodynamics extends way beyond that, and it deals with the transfer of energy, and pretty much all energy, between systems and surroundings. So it's pretty broad, and almost any kind of technology that you can think of depends or is rooted in thermodynamics, like literally almost anything, like refrigeration and motors and power plants, the computer, your phone. So many technologies fundamentally require thermodynamics to occur because thermodynamics deals with energy transfer. So it's very broad, and this is one of the most foundational fields in all of science, in my opinion. I just love thermodynamics anyways. There's a lot of buzzwords in thermodynamics, and you need to know what these terms are to truly understand thermodynamics. And the definitions of each term, the definitions may be different than common sense definitions. So I have these ones in blue here, and there'll be many other terms that I will define explicitly and carefully and in a way that you'll understand to start off with. So system or systems is whatever we're interested in. It's quite broad, but we will go through many examples of defining the system. And the surroundings is literally everything else in the physical universe. Now, I put together a very detailed video on systems and surroundings and boundaries, so you can check that out. It's pretty sweet, but we'll move on from there. So energy is the capacity to do work. You might remember this from physics class, introductory physics class. Well, what's work? Work is very simply, this is the simplest way I can say it, it's an applied force causing motion. Now we're going to go into the details of this and get more granular, and we're going to have equations and whatnot and calculations and whatnot. But very basically, if you could just have like a very simple definition, applied force causing motion. So if we were to push an elephant, then the work done on this elephant is the force that we apply, the applied force, across some distance, if it's a straight line, or displacement, if we're able to push it. That's the work. Okay, so when energy is transferred, the system changes state. So what is state? This took me a while to understand when I was first learning it. State, for a substance anyways, state is defined by certain variables, certain properties of that system. So for a substance, it's pressure, volume, temperature, the amount in moles, and the composition. And these define its state. So they're called, here, big surprise here, state variables. So for example, let's say we have a gas, some purple gas in this container right here, and we'll say it's in state 1. And its state 1, is defined by the value of the state variables. So it's defined by the pressure, which is 1 bar, the volume, which is 5 liters, and the temperature, which is 25 degrees Celsius. If we were to change the state, say we heat it up here and allow the gas to expand, it's now in a different state because the state variables have different values. Maybe the pressure is only a half a bar, for instance. Maybe the volume is 10 liters, and so it doubled. And maybe the temperature stayed the same. We'll go through this example, this process many times. This is an isothermal expansion of a gas. You don't have to know that now, just know that if we have a different state, then the state variables have different values. So there's other state variables, and we'll get to those in due time when we're ready for them. Okay, so state changes, which is the change of state, if you're changing the state, they're described by state equations, and these are also called equations of state. So let's say we have a gas and we're changing the state somehow by adding some energy as heat. Well, we can model the state by a state equation, and if this is a perfect gas or an ideal gas, the equation of state is PV equals nRT, the equation we've known and loved. This is the equation of state right here. Now, if we solve for pressure, P equals nRT over V, we now have pressure as a function of these state variables. Now, pressure here is written as a function of the moles, the temperature, and the volume, because gas is a constant right here. Now, the moles, temperature, and volume, those are state variables. Pressure is also a state variable, but written this way, we can say that pressure is a state function, because if you change the moles, the temperature, or the volume, then the pressure may change. So the value of the pressure is dependent on the state variables. So there is a little bit of difference between what a state variable is and a state function is, but if your prof might flip-flop back and forth between those two terms, they're essentially synonymous. It's just like a small difference with that. Okay, so let's get into ideal versus real gases. In an ideal gas, the collisions are perfectly elastic. There's no energy loss between collisions. They bounce off each other like billiard balls, and there's no attraction or repulsive forces between the particles. But in a real gas, intermolecular forces are present. The collisions are inelastic. That means there's some energy lost, or kinetic energy loss, like you can't just lose energy, but kinetic energy loss between collisions. And the big difference between real versus ideal gases are intermolecular forces. And that means they can be attractive or repulsive. In this case, the intermolecular forces are attractive. If you can see here, there's some clumping. See how the particles are like clumping together? They're clumping together because they're attracted to each other. There's an attractive force, kind of like magnets of opposite poles, like North and South Pole attract each other as they come closer together. And because of that, this real gas will have a lower pressure than an ideal gas. The pressure is lower because there's less collisions against the container, because the attractive forces are dominant if say the temperature is the same and the same number of moles too. Now, if repulsive forces are dominant, that means the particles are really crowded together, say like a really high pressure. And if they're really close together, then they're going to repel each other. And you can think of this as if the particles are really close together, then the electron clouds and the nuclei will repel each other as well. Actually, there's a quantum mechanical explanation we want to discuss with something called the Pauli exclusion principle and wave functions, but just like ignore that for now. Just essentially, if they're too close together, they're crowded, and there's going to be repulsive forces pushing them away from each other that an ideal gas won't have. How do we know if attractive or repulsive forces dominate? Well, it depends on the equation of state, and it depends on the gas. So for an ideal gas, PV equals nRT. And if we divide by N, we got PVM equals RT, and VM is the molar volume. So V is the volume, but Vm is the volume per mole, kind of like how many liters per mole the gas has. This is important because it's an intrinsic property. This doesn't depend on the amount of substance. The volume does. You may also see this with a bar on top like this, but anyways, this is the equation divided by N. That's for a perfect gas. So the molar volume for an ideal or a perfect gas is RT over P if we solve for Vm. For a real gas, we can just say it's the exact same equation with some fudge factor here, some Z, which means it'll be higher or lower. And Z, I say Z because I'm from Canada, you may say Z, is called the compression factor. I have a very detailed video with descriptions, animations, and things about the compression factor with a cheat sheet you can check out if you want. But essentially, if Z is greater than 1, repulsive forces dominate. And that's because if Z is greater than 1, this is greater than 1, so Vm real is going to be larger than Vm ideal, which has like RT over P where Z would equal 1. Z's not here. But if Z is less than 1, you could see this whole thing is going to be lower than RT over P, and attractive forces would dominate. The compression factor is written as the ratio of the real molar volume, that's the, I shouldn't say real molar volume, of the molar volume of a real gas divided by the molar volume of an ideal gas. So the molar volume of a real gas divided by the molar volume of what it would be if it was ideal. And if it's greater than 1, repulsive forces dominate, otherwise attractive forces dominate. Okay, so how do these attractive and repulsive forces actually work, or can we get some kind of a more intuitive sense of it? And I like to show this graph. Now don't freak out, I think this really helps conceptualize things when you think about energy transfer, and the more we can conceptualize it and have a picture in our mind, the more you'll understand it and the better you will be at thermodynamics. So this is a curve here where the horizontal axis is the distance between particles, and the vertical axis is potential energy, okay? And see these two balls? We'll just imagine these are gas particles, and when they're really far away from each other, then there's no attractive or repulsive forces between them. There's no interaction between them. They're too far away, in the limit as like infinitely far away. So there's no potential energy between them. Think of like gravitational potential energy. The more two bodies get close together, the more greater the gravitational force is between them. Well, if they're really far away, there's no, essentially zero gravitational force. It's not exactly zero, but you can assume it's zero as it gets really, really far away. And that's what we have here. So there's no potential energy difference, between them. But as they come closer together, those gas particles are going to start attracting each other a little bit more. So attractive forces are going to become more dominant. And the potential energy is going to go down because they want, you kind of quote unquote, want to come together. Think of two magnets, north and south. The closer they come together, the stronger those magnets are going to attract each other, the closer they get together. And that's because they're going down a potential energy gradient, if I can use that term, if that's okay. But then there gets to be a point where they're at that sweet spot, and if they get too close together, they're getting crowded, and you're almost trying to like push them on each other, and it takes a lot of work to do that. Think of like compressing a spring. When a spring gets compressed, then its potential energy goes up. It takes energy to compress a spring, a lot, right? Not if it's like wide out and extended, but if it's really compressed. So if these two particles get too close together, the potential energy goes up. And this is when repulsive forces dominate here. So far away, attractive forces dominate. They come together when they're far away. But too close together, repulsive forces dominate and the potential energy is high. So I got a question. How does potential energy change when a low pressure gas is compressed? Well, if it's under low pressure, then there's a lot of space between the particles. And as you compress it, the potential energy goes down. There we go. If it's under really high pressure, like very, very high pressure, repulsive forces are dominate. So the potential energy change will go higher if we compress it even more. All right, I'll leave you with, lastly, equations of state. So the perfect gas equation of state is PV equals nRT, or rearranged, P equals nRT over V. But we can model gases with different equations of state. So we can use, this is the most commonly one used in academia anyways, in your course that you may see after perfect gas. It's called the van der Waals equation. I have a pretty sweet video describing this and deriving this and talking about it and things like that, so check that out if you need to see it. This has a attractive term built in and a repulsive term built in. There's also the virial equation of state, which is derived empirically, so based on experiment that we have right here, and we'll use this one too throughout the course. And there's also many, many other equations of states that can come up depending on what gas we're using and which one works the best. All right, we're going to continue our journey of fundamental concepts, building you up step by step, little by little. I know thermodynamics is not easy to learn, but we'll do it together. And the more you come into it, the more you get through this, watch it, write stuff out, practice questions, the better you'll get. You can survive. Cheers.